Okay, welcome. I'd like to welcome everybody to our 28th SLiTHER, which is a event that we've been putting on now for about a year and a half. The Ionic Viper has been hosting these discussions, which we then record and post on YouTube. So after this this discussion, it will be posted on YouTube. And I wanted to quickly share, note that if you want to access any of the previous recordings, including this one, you can go to our website, www.ionicviper.org, and we have a collection under content collections. There's a collection of all of the SLiTHERs that we have had so far. And so after this one is recorded and posted, it will be there. So here's just really quickly, I wanted to show under content collections, we have collections of learning objects from our site, but SLiTHERs is specifically one of them. And so, for example, if you wanted to go back and look at where we started and where we've been, these links all link to all of the YouTube videos for each of these SLiTHERs. So with that, I'm really excited today because we have Dr. Ulrich Fekl, who is a professor in Canada at the University of Toronto, Mississauga. I hope I said that right. We're excited to learn about this paper that he recently published that he'll be telling us about. And so just as a reminder, if people have questions, throw them in the chat and we'll have time for discussion afterwards as well. And with that, again, I'd like to welcome Ulrich and go ahead and take it away.
Thank you, Kyle. Thanks for the invitation to speak today at this SLiTHER. It's really a wonderful opportunity for me to tell what I have been writing related to my teaching recently and what I have been teaching for a couple of years. And that particular topic I would like to talk about is valence bond theory, in particular SD and sd2 hybridization for transition metals. I'm switching to screen sharing right now. So you should see now my screen here. And so that is a topic, SD hybridization, sd2 hybridization. What can we do with it and why is it useful actually to teach to undergraduates? So in a nutshell, here is valence bond theory for the D elements in literally one slide, the history. Very popular in the 1950s, sp2d or dsp2 hybridization for square planar 16 valence electron, sp3d2 for octahedral complexes, introduced by Linus Pauling, looked very compelling at the time. Unfortunately, it is and was shown to be inaccurate, and this is unfortunately leading to decreased use of valence bond theory in transition metal chemistry. So there was too much of a backlash against that because it was shown not to be true. And it was shown not to be true simply because the valence shell p orbitals were too high in energy. So they're not really involved to much degree in the heavier D block elements. So for the first transition metal row, there's a little bit more of P contribution, but for like a second or third row, like palladium platinum, there is very little. So every time you find sp2d, it's wrong. It's wrong for the main group elements because there the D is not available. It's wrong for the D elements because there's a P not available. So we're talking here about D elements. So if we simply cross off, sorry, I have to switch back here. It's move too fast. If I cross off the P contribution, I get the correct hybridization scheme. That is a quick and easy way, of course, that needs quite a bit of an introduction to see how to get there in a more rigorous manner. But really SD and SD2 has not made it into undergraduate textbooks. And I was watching the literature, it hadn't made it. So I decided to write it up. So my personal history with this topic is I read very soon after it came out the book by Weinhold and Landis, Valency Bonding. I found it a total eye-opener. It really is very enlightening about bonding in transition metal complexes. I played a bit with Gaussian. I didn't go beyond with NBO. I didn't go beyond with what's in the Weinhold Landis book, but that's definitely worthwhile reproducing that. That is indeed repeatable. And I started that very soon in Toronto as a method in my third-year course. And it's literally less than an hour. Today I spent like 30 minutes on it. And it is for most students very, very intuitive. And I was watching the literature. It hadn't been published for undergraduate teaching. So I finally got the time to write it up, in here it is, Journal of Chemical Education 2021. So for the following, pretend you're a student in my third-year class, and your background is you come from the second-year inorganic course, which is in Toronto, taken by many students. So second-year inorganic isn't common in all places, in particular in the US, but in Canada, many places have inorganic in second year. So I have to mention that. And in the inorganic second year class, I'm already talking about hypervalent bonding. The students know that I2 adds an iodide to make I3-, not a complicated MO scheme needed. A sigma star is being attacked by a lone pair on I-. So you get that beautiful 3-center 4-electron bond. And now pretend you have this background. You're now in my third-year class, and I have taught 2 lectures so far. I introduced organometallic chemistry with the ligands like methyl-, H-, a hydride ligand. And we practiced valence electron counting. So in that exercise, you counted to 12, 14, 16, 18, 20. But you might wonder now, what is a common d-electron count? So this is now lecture 3. So welcome to today's lecture in transition metal chemistry. Last time we talked about valence electron counting, and you counted all sorts of numbers, 14, 16, 20, 18. And you might wonder, are these realistic examples, or what numbers can I really expect to see very commonly? Like in main group chemistry, you're expecting to see the number 8 quite frequently, simply because of the octet, but be aware, and you are, there is a very common so-called octet expansion, like you've seen in your lab, where you meet ICL3. We discussed I2 being attacked by an iodide to make these 3-center 4-electron bonds. So we are expecting to see some numbers, but don't take them as a law, right? And we will use a valence bond approach pretty much like you're used to from main group chemistry. And that works quite well. So valence bond approach for the D complex compounds, the thing to keep in mind is S and D hybridization. Forget about the P. For your valence shell, the p orbital can be safely neglected as contributing to your hybridization scheme. So that is knowledge known in the graduate level literature. It unfortunately hasn't made it in the textbooks for undergraduates. So that is something to keep in mind here. For example, 3D4S is for your first transition metal or your valence shell. Forget about the 4P. If you're talking about palladium, 4D5S is your valence shell. Forget about the 5P. And then you should practice a rather unusual thing. Draw a Lewis structure of your organometallic complex. It's rarely done. It is actually fun and interesting, and it's also not in the textbooks. So we will draw transition metal based Lewis structures with all electrons. And it will be equally straightforward as main group chemistry. This is why I'm showing it. Like main group chemistry, let's discuss the structure of ammonia as a little warm-up exercise. Very simple problem. Structure of ammonia, how do we get there? Oh, sorry, that's switched forward. Here we are. NH3, nitrogen, group 5, 1, 2, 3, 4, 5 electrons. So I'm creating here a Lewis dot structure of ammonia, and here we are. That is a Lewis structure for ammonia. I prefer to write lines instead of double dots. It's just faster to write. So here you have the Lewis structure of ammonia. And what might your bond angle be? Well, let's look at the valence orbitals involved. This has to be on the same level, obviously. Valence shell S, valence shell P. And the important message is for the first row of p elements, valence shell S and valence shell P, are of very comparable size. So they can mix quite easily and make hybrids. So you end up with this iconic set of 1, 2, 3, 4 sp3 hybrids. 4 times sp3. And your structure is very well described if you say, I have a lone pair in one of the sp3s, and I'm using the remaining sp3 hybrids for bonding to hydrogen. So that was the easy warm-up exercise. Let's just highlight this here in a different color so it doesn't interfere with my drawing. So that was an easy exercise, but now comes a really difficult problem, pH3. Okay, let's draw a Lewis structure of pH3. Okay, what is the bond angle alpha in pH3? If you go back to ammonia, it's sp3, so your angle is roughly 109.5. I think it's 107, very, very close to the ideal sp3 angle. In ammonia, we measure very close to what is expected from sp3. Experiment 107. Okay, pH3, what is the bond angle in pH3? Well, I heard an answer. Somebody said 109.5. That is very tempting. Unfortunately, that is wrong. So in pH3, we have to think a little bit deeper. So we have a orbital scheme for the valence shell orbitals that is very, very similar. So we now have 3s and a 3p. And you could say I'm making hybrids, but that is actually not what happens. The reason is the valence shell S is more contracted. It's smaller than the valence shell P for all the heavier p block elements. So the first row of p block elements is unusual, that S and P are of similar size. Not only is S lower here in energy than P, we saw that similarly for ammonia, but it's actually smaller, less prone to mixing and hybridizing. Okay, if we know that, what can we do? We have the Lewis structure of pH3, and we have to put our lone pair somewhere. The lone pair isn't stabilized by bonding. So if it isn't stabilized by bonding, we want to put it there where it is already low to begin with, particularly since this s orbital avoids hybridizing unless it really, really needs to. So let's put our lone pair in the pure S. So that would be the lone pair in the pure S. And now you're done. Our pure p orbitals will be used in the bonding to the hydrogens. Okay, so that is indeed the structure of pH3. Phosphine with 90-degree angles between the hydrogens. So theoretically, 90 degrees. Experimentally, I think it's 96, or I think it's 93. Let's just look it up so I have the exact number here. 93.6. 93.6. It's really, really close to 90-degree angle, and much closer to 90 degree than to an sp3 109.5. So that would be like pure P, and let's just label them in different color. Px, Py, Pz, relatively pure Px, Py, Pz in the bonding orbitals, and your lone pair is approximately pure S. Okay, so with this little slightly more complicated exercise in mind, we are able to tackle hybridization in the D element compounds. So who can show me a Lewis structure of platinum dimethyl? Nobody's volunteering. I tell you why. It feels weird because no book actually shows you Lewis structure of d-element compounds. But why not, right? Why not? Platinum atom has 10 valence electrons. So platinum 0 is d10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Let's make platinum dimethyl, attach a methyl radical, attach a methyl radical. Here we go. Here's your Lewis structure, or if you draw lines instead of double dots. Valid Lewis structure for platinum dimethyl. Great, but what is a bond angle? We're saying we want to predict the structure correctly. What is your bond angle alpha, your carbon platinum carbon bond angle? Should it be linear? It should be linear, right? The methyls want to avoid each other. Is there any electronic reason for it being bent? Is it tetrahedral? Is it 120? How do we approach that problem, right? The solution is really completely analogous to the pH3 problem. You draw the orbital energies 1, 2, 3, 4, 5. So you have your valence shell D. Here's your valence shell S. And now keep in mind, similar as in the pH3, the S was more contracted, though the D is more contracted. So I have to switch back here, that went forward too fast. So D is more contracted. There is a pressure to avoid hybridization. It's smaller in size than the S. Okay, so if you start with a Lewis structure and you know you have lone pairs, and there's a set of atomic orbitals that are contracted relatively close to the core, compared to the S at least, and lower in energy. This is exactly where you put your lone pairs. Let's do it. 1, 2, 3, 4 lone pairs. So we have D lone pairs. D lone pairs. And we have left for bonding an S and a D. So these will now be used in bonding to two identical carbons. So now hybridization is in order, and we're making 2 SD hybrids. So that is indeed the correct hybridization scheme for platinum dimethyl. Let's just put it here in writing, pure D lone pairs in this correct Lewis structure of platinum dimethyl, and we have an SD hybrid used in each of these bonds. The only thing we need to answer now, what is a shape of an SD hybrid? And my derivation here isn't rigorous, but I think quite intuitive. Take any of the cloverleaf d orbitals. And if you take one and the same cloverleaf shaped d orbital, and you add an s orbital directly on top, then you get one SD hybrid. And how can you make from exactly the same 2 orbitals you're using a second hybrid, right? Because you go in with 2 orbitals, with 2 atomic orbitals, you have to get out of your mixing with, again, 2 orbitals. So there's only one way to do it. If in your first mixing you used a positive phase and a positive phase, now in your second choice, you have to now use an opposite phase. And you end up with these 2 SD hybrids that are oriented at 90 degrees. So that orientation at 90 degrees comes out of very, very rigorous calculations. It's not only my hand-waving derivation here. Again, like hybridization is just adding the wave function values at the same spots, so at the same nucleus, add these two to it with 2 different phases, and you can't help it. They come out at 90 degrees. So here we go. So we have a correct structure prediction for platinum dimethyl, CH3, SD hybrid here, SD hybrid here, lone pairs are pure D, and your angle here is 90 degrees. Quite a surprising result, holds up to rigorous theory if you run your own geometry optimization. Okay, the platinum dimethyl is bent at 90 degrees. Can we make platinum dimethyl? It's actually quite difficult. You would have to make it in the gas phase. How do you do that? But if you make it in solution, you have THF around, or dimethyl sulfide, or dimethyl sulfoxide, and you will have coordination of solvent. So how will other molecules now coordinate to your platinum? I'm sketching here again one of these SD hybrids with these little side lobes, which are chemically not meaningful, but they're there. And I'm showing you now interaction with the orbital on the methyl group, like in roughly sp3 hybrid on the methyl group, to make a bond. Now it turns out in that interaction, you know from MO theory, you can't help it. Every time you make a sigma bonding orbital, you also will make, whether you like it or not, a sigma star anti-bonding orbital, which I'm showing here. So you have this anti-bonding orbital that has a very large lobe on the back side, right? Simply because of the symmetry of the sd hybrid. The back side has a very large lobe, as large as the front side. This is why that is susceptible to attack by added ligands L. So other ligands will now bind trans to the existing bond, and your interaction will be a 3-center 4-electron bond. You do that twice. Let's do it in sequence. You take a platinum dimethyl and you bind one ligand first, and you get a T-shaped arrangement. That's a correct prediction. So the T-shaped structure is more stable than the trigonal planar structure. You add another ligand and you get a square planar structure because the remaining ligand adds trans to the remaining PTC bond. A rather unusual way, but a powerful way to derive that platinum 2 dialkyls are square planar. Another thing that comes out of this derivation is that cis geometry will be more stable than trans, because in the underlying covalent framework, in the cis geometry, both methyls that are covalently bonded have their own sd hybrid to bond to. And in the trans, the two covalently bonded ligands would have to fight for their own, would have to fight for one and the same hybrid orbital at platinum. So as a cis geometry, you maximize covalent bonding to the two strongly bonded ligands, and the donation into the sigma star of the bond now happens by the more weakly coordinated ligands. So cis more stable than trans, nicely explained by this localized bonding approach. There are, of course, many, many examples of square planar platinum 2 dialkyls. Here is just one with a cod cyclooctadiene. So you have these double bonds donating trans to a PTC bond, trans to a PTC bond. That effect, again, you're donating into an orbital that was anti-bonding with respect to the initial bond. That really means if you make one of these trans interactions stronger, you're making the other one weaker. That effect is known as trans influence, clearly seen here in that example I took from Dick Pudefat's literature. In the right-hand example, you can see the highly covalent carbon has a more weakly bonded nitrogen trans to it, where the bond length is now longer trans to carbon as opposed to trans to chloride, because chloride is less covalent. And on the left-hand side, you see water more weakly bonded, and that has an even weaker trans influence here. Okay, moving on in our little exercise of drawing Lewis structures for d-element compounds. Let's draw a Lewis structure for iridium trimethyl. Iridium atom has 9 valence electrons, 1, 2, 3, 4, 5, 6, 7, 8, 9. I attach 3 methyls, CH3, and what do I get? A valid Lewis structure for iridium trimethyl. Hybridization scheme, straightforward, 2, 3, 4, 5. Let's redraw that level. Here's D, here's S. Where do we put the lone pairs? We avoid mixing, we put them into pure D. Here we have 1, 2, 3 pure D lone pairs. And now we have 3 valence orbitals left to bind to these 3 identical methyl groups. And now S plus D plus D. These will hybridize now into make 3 sd2 hybrids. 3 sd2 hybrids, how do they look? I'm not deriving it here, but it's easy to remember. They're also symmetrical dumbbells, little side lobes I will omit, and they are also oriented at 90 degrees. So S1D2 hybrids are also oriented 90 degrees, all 3 against the other one. That means they are oriented like the X and Y and Z coordinates of a Cartesian coordinate system. That gives you the structure of iridium trimethyl. It has this highly angled wedge-shaped arrangement. CH3, 90 degrees, 90 degrees. And your 3 lone pairs in that valid Lewis structure, where the lone pairs are in a pure D. Experimentally, this is indeed hard to observe because other ligands will bind quite easily. But here's a beautiful experimental structure from Geoffrey Wilkinson's group, and that is iridium trimesetyl. So mesetyl is just a trimethyl phenyl. Phenyl is really like isoelectronic to a methyl minus. So this structure wants to be bent, wants to be angled, not platinum, it's iridium, right? It really wants to be bent, carbon, carbon, carbon. And the reason the angle widens here is due to sterics. So it's a 90-degree theoretical ideal angle widened due to sterics. So mesetyls are extremely large due to these ortho methyl groups bumping into each other. The sterics prevent this from being 90 degrees, but it's still very narrow at 107. So Geoffrey Wilkinson's group back then wondered, how come that looks like a tetrahedral angle that is narrow, right? How can bulky ligands make a tetrahedral angle even narrower than 109? And so they couldn't answer it in 1992. We know what the answer is. It wants to be 90 degrees. It's actually not a tetrahedral angle electronically. It wants to be a 90-degree angle, and it's opened up to an almost tetrahedral angle due to steric pressure. Okay, so what did we see here in these D6 iridium triphenyl or iridium trimethyl compounds? We have again a very interesting energetic prediction that these 3 carbons want to be in that their own sd2 hybrid. We can all use their own sd2 hybrid to bind to iridium in the most covalent fashion. And trans, of course, you can have additional ligands donating into the sigma star. And you end up with this very common octahedral geometry, right? But a very uncommon derivation of the octahedral geometry, starting with a metal R3 fragment. And these compounds are very important. For example, your ligands might be tied together in, I think I started wrong here, in these cyclometallated complexes. Yeah, that's better. These cyclometallated complexes, which are used in emitters for LEDs. Let's just spell it out here, like these NC. Emitters, you will have more stable than the meridional one. And the reason is, again, because you will maximize covalent bonding if you do C. No, it's right. And the other ones are N. Let's just do that here in red. Yeah, so a Fekl isomer is more stable than the meridional isomer, and we know now why. So this is kind of concluding the lecture on sd hybridization. We know why the 18 valence electron count is very common for octahedral D6 complexes. So in terms of the electronic description, we actually have three center 4 electron bonds, which happens to be a very stable situation. Square planar D8 complexes, also a very stable situation. We have seen we have 2 3 center 4 electron trans interactions, both 2 very, very common valence electron counts. And finally, let's look at D10 systems. So your method works just the same. 1, 2, 3, 4, 5. Here's your D. Here's your S. Let's take a palladium atom. It's D10. Where do you put your lone pairs? As low as possible, pure D. Pure D lone pairs, and the S is your acceptor orbital. So we really have only one acceptor orbital for these D10 systems. And you can say, for example, you add one phosphine PR3. Now you have a 12 electron normal covalent compound that is a 2 center, 2 electron bond. And what orbitals are involved? Well, you have an s orbital at palladium that's empty. And you have your phosphine donating into that empty orbital, right? But you can already see what can happen here because the s orbital is round and symmetrical and there is plenty of space. So you can also have P3, 3P, 2 phosphines donating into the same s orbital. That would be now a 3 center 4 electron interaction. You can compare it, for example, to F minus, H plus, F minus, called bifluoride. That's also a very stable, highly symmetrical 3 center 4 electron system. Or you can, of course, now add even more phosphines. Let's just do that here. P3, 3P. And you have a 4 center 6 electron interaction. or you're adding one more phosphine, 3p4 palladium, and you have a 5 center 8 electron interaction, and each subsequent interaction gets weaker and weaker because there was already donation into that formerly empty s orbital. So you have a law of diminishing returns. Let's just do the valence electron counting here. So that would be a 12 valence electron example. That would be 14 valence electrons. That would be 16 valence electrons. And that happens to be 18 valence electrons. There is nothing special about 18 valence electrons in D10 systems. In fact, in D10 systems, 18, 16, and 14 are all very common. And you will actually see these in catalysts you purchase from Stram Chemicals that might be actually 3-coordinate or 2-coordinate and even 1-coordinate. And definitely in your catalytic cycles in the subsequent lectures, you will see 18, 16, 14, possibly even 12 valence electron complexes that are D10. So these are common valence electron counts. And now you've seen where they come from. Thanks for listening. Okay, so that was how I would teach it in my lecture. I like teaching that because I think it solves quite a few problems. It's just fun to teach Lewis structures because it's just not done typically in textbooks. And it explains the trans influence very, very clearly, Fekl versus meridional isomers, and so on. If you add ligands stepwise to the low coordinate fragment, you get a seesaw structure, you get a square pyramid. So it's great that Karen is here because the 5 coordinate platinum 4 complexes have been all square pyramids. So it's hard to prove with an MO scheme. It comes out of this quite beautifully. Any questions, ideas?
Yeah, that was great. Thank you, Ulrich. And so the rest of our time is open for discussion. So if you want to, again, anything about the discussion or the paper, again, this JChem Ed paper, I found the paper when it was still in Chem Archive and reached out to Ulrich because I was like, this is awesome. But yeah, what are your thoughts?
Yeah, Ulrich, fantastic talk and
Thanks,
fantastic
Nancy.
paper. This explains a lot of things that I've been trying to explain since I was a wee grad student and have not made sense for a long, long time. And I think the combination of thinking about this bonding as 3-center 4-electron bonding and recognizing the lack of involvement of the p orbitals really helps to explain a lot of chemistry. I also appreciate that you went from very early metals at iridium to very late metals at palladium. I was expecting you to go to gold 1, but I appreciate that you kept a narrow focus there.
Yeah, I did it in the paper. I mentioned gold
Right.
1 in the paper. Yeah.
No, but sorry, this was three comments and a trench coat rather than a question. But the question that I really have is that if you think about this in terms of classic 3-center 4-electron bonding, right? The place that we think about this the most is resonance in organic chemistry, right? The pi system of acetate. And that's
I do that. I do think like that.
Yeah.
Yes. Yeah.
The most stable arrangements in those cases, and also in the p block where we see this in hypervalence, like SF6, the most stable arrangements are actually the symmetric ones.
But
Right?
it's not.
Because you get the Huckel root 2 stabilization of the resonant bond by delocalizing over 3 centers. So that ends up usually winning, right? There are lots of cases where you do get these asymmetric cases and one resonance structure is better than the others, but the best stabilization is always the symmetric one. And yet it seems like in these transition metal cases, the most stable one is the asymmetric. Right, it's the dialkyl and then di-L ligand where L is something like ammonia or a phosphine or something much weaker. Do you have any thoughts on why it is that in these transition metal systems there seems to be a preference for being closer to the 2-electron, 2-center bond with a donor into the antibonding orbital end of the
I see your point. I see your point.
and not as much favoritism toward the symmetrical, more delocalized bonding.
I mean, a point could be made that even in main group chemistry, the hybridization does lead to a lowering of symmetry. Like if somebody hasn't seen main group chemistry and draws pH3, they might draw it as planar, which would be more symmetrical. So you actually have a lowering of symmetry due to the correct hybridization. But you do have a point here. You have these fragments where often they're kind of lopsided, right? Like Fekl trialkyl, cis dialkyl. That's a good question. I have a hunch here that it could be the type of the central orbital and its symmetry. Like we have a G-type orbital for the D elements, like we have in these sd hybrids. They have G symmetry, and for the for example in I3 minus, we have of course a p orbital in the central atom, which has U symmetry. So there could be some impact of that. I haven't really thought about that too deeply. Why is it more lopsided in transition metal chemistry? There's a related paper, so it's kind of a little bit evading your question. It's not a direct answer, but my colleague Bob Morris at Toronto, he has a very recent paper on symmetrical versus anti-symmetrical stretches, and he finds that it depends on the symmetry of the central orbital being used in that bonding, and it's exactly the opposite for the D block and for the P block. So it's conceivable that an argument like that is valid here. I haven't thought about it deeply, but I see your point. If you have something like SF6, that is a very, very stable symmetrical structure, and if you were to make platinum hexamethyl 4 minus, that would be much, much harder to make.
But we actually do see both in the main group now that I think about it, right? Because you have PF3, to take the phosphorase example, and that's
right.
And it's stable.
Yeah.
We also have PF6 minus, right? You can do both. But what
I guess
we don't have is PH3 F3 or something like 3 minus. Yeah.
In all fairness, there's more being discovered, right? Sometimes main group people discover things. I think there's now the first hypervalent fluoride that was just published a year or two. Perhaps perhaps it's not a law of nature. Perhaps we haven't really looked at the right compound.
Karen had asked in the chat if there's some way to connect this type of lecture to the isolobal analogy.
Oh yeah, no, sure. So yeah, that is really an important question, and I address it in that paper I wrote. The reason is I'm teaching the isolobal analogies, which I love. They're amazing, and I'm teaching that SND hybridization on purpose first, and then I make a connection to very stable hypervalent main group compounds. So essentially, I fully agree with Walt Hoffman's analysis that octahedral D6 complexes should be considered isolobal to methane, right? And if you have 18 electron Ml6 and it's isolobal to CH4, then you can derive very, very useful things. For example, that a 16 electron Ml5 is isolobal to a methyl cation. So you have a very strong electrophile. And these are really, really useful rules. And but from these rules comes a potential misconception. The misconception is because 18 electron Ml6 is isolobal to CH4, and in CH4 every bond is a 2-center 2-electron bond. So the misconception could be that in 18 electron Ml6 now every bond has to be a 2-center 2-electron bond, and that is not true. And to avoid that misconception, I teach first sd hybridization, and then I make the point that 18 electron Ml6 is a very stable closed shell compound. So closed shell in the sense there is no low-lying orbital that's not filled. There are all anti-bonding orbitals actually empty. So it has it in common with CH4. This is why we can use an analogy. And I make the connection through SPF6 minus. SPF6 minus would be also a very stable closed shell molecule, but it's also hypervalent. That it's not a contradiction. It can be hypervalent in closed shell. So if you take SPF6 minus and you remove a fluoride, then you get SPF5. It's the same as removing a hydride from CH4 and making CH3 plus. So essentially all closed shell species are isolable to each other. And that doesn't mean the bonding is exactly the same in all these species. So that's a very good question. That is a link to the isolable analogy.
Yeah. So my question is, how do we get rid of this stuff? And you can't see it, but it's the wrong hybridizations, right? So all of the books I went through and looked at all of my inorganic and Gen Chem books, and they're all teaching sp3d2, right, and stuff like that. Even MFT.
Yeah, so basically the problem is that word hybridization is used in different ways, and that's not always made very clearly. So you actually compute an accurate wave function, and then you look what orbitals are involved to which amount in a localized picture. And that would be the rigorous use of hybridization. And sometimes people use hybridization as a shorthand for geometry. They're essentially saying sp2 when they mean trigonal planar. And that is a confusion that can be avoided by essentially literally talking about geometry when you mean geometry, and people shouldn't use hybridization terminology. For example, if you have a palladium 0 with 3 phosphines, it's trigonal planar, but you should not call it sp2. So yeah, that's annoying, but I guess we are educators. All we can do is we can basically write about it, blog about it, talk about it, and hope that it eventually makes it into the better textbooks. Yeah.
So are there any Gen Chem textbooks that don't do what we're all arguing against?
I mean, not the ones I've taught out of.
Are there any? Does anyone know of any?
There are some that have at least backed off of using d orbitals to explain hypervalence in the p block. I haven't seen any that take the p orbitals out of the d block. Dean, do you know of some?
Yeah,
or you look like you were about to jump in there.
Yeah, McMurray and Fay, the atoms first doesn't do. They only go up through sp3. They don't do any, so they just don't talk about it. But they do have some problems where they ask students to draw Lewis structures of transition metal complexes, of very simple ones.
They do? They do or they do not?
They do, but not hybridization. They'll just throw in a transition metal and early transition metal and have them treat it like they would a main group.
But if they only stick to sp3, do they stop at the second row, or do they also go into the?
Well, no, they do octet expansion, but they don't do it in terms of hybridization.
Yeah, but I mean, most books like that, they just like stop at sp3, or they'll just say, oh yes, it's sp3d2 for octahedral. Like it is. Like no, it's not. So that's one of the things that I liked about this. So.
I mean, one of the other challenges is that we still want to use VSEPR.
Yeah.
Right, which I'm convinced has outlived its usefulness, and we should claw back that week from the Gen Chem course and put in other stuff, because it's not like that course isn't already too full. But the argument is always, well, you can't take anything out. Well, here's something we could legitimately take out because it's wrong and it's not helpful.
Does any of this stuff make it, though, onto exams that students take later, whether it's MCATs or just even placement exams in chemistry, like even the ACS exam? Does this show up? I don't know. I haven't looked at it.
No, we should. I mean, that would be a thing, is we can like chat with the ACS office, exams office, say, hey, we want to make sure this like recently being 4 decades ago, corrected misconception is no longer in our exams. Right?
Right, because you don't want to put in a position where you take it out of the class and then it shows up on an exam, and then the student's like,
yeah.
We also got to get the double bonds to phosphine and phosphate and sulfate out of the organic and biochem textbooks.
Well, there's 3 double bonds in perchlorate, right?
you know, we can't even get phasing into the Gen Chem orbitals. So,
anyways, but yeah, so I'm excited to teach this the next time that I teach inorganic, because yeah, it was kind of an eye opener. Also, I don't know if for those of you on the Discord server for Ionic Viper, which if you're not on, you should join. Like I went and did NBOs, and it's just, yeah, platinum dimethyl. It doesn't matter what theory you use, as long as it's a decent theory, the same answer comes out, that it's SD hybrids. It's like, oh man.
So what do you do in a general chemistry class when this is in the textbook and this is being taught and they're expected to know that, and you're part of a whole group where everyone is teaching? I mean, what is the course of action?
Yeah, well, then you stick with the book, unfortunately, I think. But you have to, like, so for example, I know some people are moving to open textbooks, and then you can kind of pick and choose sections or modify sections even if you can do your own. But that takes some work. And so speaking of SLiTHERs, there was a SLiTHER on using LibreText in inorganic, and that was which is an open access text. I know that some people use OpenStax for Gen Chem, for example. So there's movement in a direction that would allow for more instructor control over the specifics in the textbook. Yeah.
Yeah, on that specific problem, Karen, I fought the law and the law won this year because I'm teaching Gen Chem. But I'm teaching accelerated Gen Chem all by myself in the spring, and so I'll teach it differently.
Yep. And yeah, we need to get some LOs on stuff like this and on Viper, and we need to get, the more that gets communicated, and again, thank you, Ulrich, so much for coming and sharing this again here with Anne, for publishing the paper, because I think it's a great thing to get out there. Anybody else have any questions or comments they wanted to share?
Yeah, I mean, we should do ourselves a favor and stop drawing MO diagrams for ML6 complexes that involve those p orbitals.
Yep.
Because all the inorganic textbooks still do that.
Yep.
And we've known for 40 years that that's wrong, and yet we all still do it in all of our textbooks, and we're a community that actually talks about this to each other.
So I couldn't hear my internet.
Yeah, so Ulrich, we were talking about, Nancy was saying that we should work on getting, correcting the kind of inclusion of p orbitals, right? Like the big issue, right? The first thing you did in your lecture was knock out p orbitals, and there are still books.
This is the issue, yeah.
There's still books that have that, so yeah, we need to.
I think all of them have it. Right?
Yeah.
When they draw the ML6 MO diagrams, the p orbitals are
That
always
is-
included.
that
and they
is
should be.
everywhere.
Well, maybe this is the next.
In terms of symmetry,
Until you said it, Nancy, like I hadn't even made that connection yet to this whole thing.
Yeah, so maybe that's something that the next JChem Ed paper.
in terms of symmetry,
And when you do that,
Yes.
then your ML6 diagram comes out with bond orders of 1/2 for all of your sigma bonds and transition
That's right.
metals, which
that's correct. That's what it is. It's a
completely
bond order of
lines up with all
1/2.
of this. It explains why the bonds are half as strong. It explains
Yeah,
why
everything makes sense.
native bonds look different than regular covalent bonds because they're kind of half not there and they're half lone pairs sitting on the ligands.
That's a good summary, yes. So, I mean, the p orbitals have the right symmetry. So in terms of, if you're only, an MO diagram is overemphasizing symmetry. So everything that has its right symmetry formally mixes in, but how much of an effect it actually makes, you wouldn't easily see from the MO diagram. So
Yeah,
It's
but
not-
I mean, I don't draw platinum's 1s orbital in my MO diagram. It's the right.
it's true. Right? If it has its right symmetry, but it's energetically not a factor, it shouldn't be there. Yeah.
All right, so I don't want to take people's time. We're about at the end of the hour, but thank you all the attendees for coming and listening. And if you want to share this with your peers or friends or colleagues, we'll have the YouTube video up. Usually takes a couple days to get it recorded and make sure the recording's all good and processed and uploaded and stuff, but a day or two. Again, thank you again, Ulrich. It's been great. And